Thus far, we've really looked at concentrations and solutions in a rather qualitative way, but there is a very quantitative nature to the concentration measurement. We can tell exactly how much solute there is per amount of solvent. We can define this relationship numerically. And here are a few ways that concentration is represented in healthcare. You might see it with just a percentage. This would be the mass of the solute per 100 milliliters of water. You might see it as some other mass per volume measurement, or you might even see it in terms of millimolar, which is something we haven't talked about yet, but we will for the rest of this module, which describes not the mass of the solute, but the particles that are present per amount of total solution. And again, I think that this is a really good place to start. We're going to describe these three pretty soon, but the point is that conceptually, they all describe the same thing. How much solute is there for how much solvent? It's the relationship between solute and solvent that we seek to describe, and all three of these could be used to do that, are used to do that. So let's talk about percent solutions. And again, this is really very common in IV fluids, topical medications. We have a picture here. We talked about this 0.9% sodium chloride isotonic solution already. The percent here means grams of the solute per 100 milliliters of solution. So here, when we're looking at this, it says 0.9% sodium chloride. What that means is that for every 100 mils of solution, not 500 that it says on the bag, but for every 100 mils of solution, we have 0.9 grams of sodium chloride. That's the recipe for this isotonic solution, is that if we have a certain amount of water, 100 mils, we need to put in 0.9 grams for every 100 mils. Now, this bag says 500 mils because we have more than 100 mils in the amount that we need to distribute. Just because the relationship says 0.9 grams for 100 milliliters doesn't mean we couldn't have a little cup full of this stuff, a 100 mil bag, a 500 mil bag, or an entire swimming pool full of normal saline. As this bag is 500 mils, we now know how much salt we need to add in order to get to this concentration. And that is a problem that we're going to be looking at soon, right? Kind of in a napkin mathy way, 0.9 grams for 100 mils means that if we need 500 mils, 5 times that much, we'll need 5 times as much solute as well, because we have 5 times as much solvent. That would be 4.5 grams, 0.9 times 5. That's the amount of salt that's in this 500 mil bag. But again, this percent refers to grams per 100 mils, and if we look at 5% dextrose, D5W, this is 5 grams of dextrose per 100 mils of solution. 0.9% NaCl, normal saline, is 0.9 grams per 100 mils. It refers to 100 mils of solution because 100 mils of solution has a mass of about 100 grams. Okay, what about some kind of mass per volume? This is probably the most practical method for medication administration because it does much more explicitly say the volume unit that's being used, right? This percent solution, it's like nice and colloquial and it's easy to say, well, you double it, the percent doubles, but it is a little bit confusing what the amount of solvent it's referring to is. You really kind of have to memorize that it's 100 mils of solution, and the reason that that gets to a percentage is because 100 mils of water has a mass of 100 grams. But you'll often see mass per volume where it's just kind of said explicitly. Milligrams per milliliter, milligrams per deciliter, things like that. Some examples are here, and these numbers tell you how many milligrams are in 1 milliliter for this morphine example, right? It says units, milligrams per milliliter. If the units were different, it would be telling you different mass and different volume units. And so this is really useful because it plugs right into our dimensional analysis. So can we use dimensional analysis for the dosage that may be required? And the answer is definitely yes, and I'll show you how in a second. If what is ordered is 20 milligrams of morphine, right? That's the amount of drug that needs to be delivered. But all that's available is this morphine solution, right? We don't just have solid morphine sitting around the hospital. What we have is this solution of morphine for which every 10 milligrams, every milliliter has 10 milligrams. It's 10 milligrams per every 1 milliliter of this solution. 10 milligrams of morphine for every 1 milliliter of solution. How many of these do we need to apply for the patient? Again, the order is 20 milligrams, so let's start there, use our dimensional analysis. 20 milligrams, we want milligrams to cancel out, so we can use the concentration as a conversion. Milligrams cancels with milligrams, leaving us with milliliter unit, and we see, well, it's 2 milliliters that is required for this patient. Now, when we're dealing with conversions and things like this, there are a lot of ways. Oh, we remember we divide here, we multiply here, but this is a great opportunity to continue using your dimensional analysis. Concentration really is a conversion. It tells you that when we look at one vial of this morphine, if we have 1 milliliter of it, that's equal to 10 milligrams of the drug. And those two things are equivalent and can be used in dimensional analysis to solve in this exact way, right? If what's available is 10 milligrams per milliliter, this patient's dosage would be 2 milliliters of this solution to get to the order of 20 milligrams. Okay, the last way that we want to track concentration, this is a little bit different, but this is through number of particles. But the challenge is that there are an awful lot of particles in a milligram, a gram, whatever the amount that we're dealing with. And so in chemistry, we use a unit called a mole. And we're not going to get too into a mole in this course, but it's like a counting unit. It's like a dozen. It's literally a number, and it's a large number. By using this large number, we can track large numbers of particles. So when we say mole per liter, millimoles per liter, whenever you see moles, what you want to think is number of particles, like actual atoms, actual compound molecules, things like that. We also refer to a millimole, and this is just 1,000th of a mole, right? Milli is 1,000th, milligram is 1,000th of a gram, millimole is 1,000th of a mole. And we use the millimole because in blood chemistry, a mole is like quite large, and it ends up leading to a lot of decimal values that we would have to deal with. More convenient to use like counting numbers rather than decimal values. Here's some tests. If we're looking at a patient, right, we have sodium, potassium, and chlorine, and we have the following numbers. We have the reference range, and these units are all in terms of millimoles per liter. This refers to the number of sodium, potassium, and chlorine particles, not the mass of sodium, potassium, and chlorine, but the actual number of particles per liter of blood. So that's what millimoles per liter means. If we have a potassium level of 4 millimoles per liter, that means that there's 4 millimoles, which again is a measure of the number of actual potassium particles in 1 liter of blood. Here are some levels and ECG changes that show what happens if our potassium K+ is outside of the range, right? We're looking for 3.5 to 5 millimoles per liter. Elevated is associated with some changes to ECG, as well as too low is associated with other changes. And by tracking levels in terms of this concentration unit, we can explain, diagnose, and just better understand a patient's healthcare condition.